So you may wonder, where is Dr. Shi? She's having an emergency, meeting, and that cannot be moved for the first hour, so she could not join, but she will be able to join, say, at 2 p.m. Okay, so today I would like to speak about the material and talk about high-dimensional modeling, especially about regression. By the way, my name is Anru Zhang. I'm an associate professor at the Biostudies and Bioinformatics department and the computer science department. And it's my great pleasure to talk about, to teach this lecture. Okay, so here's a summary of what we need to do, what we plan to do. We want to introduce the principal component of regression, and we want to demonstrate how we can implement this using R. And later, I think Dr. Shi may also introduce the penalized regression models, including the rich regression lasso, elastic net, and again demonstrate how to implement using R. And then Dr. Shi might also introduce the concept of cross-validation for tuning parameter estimation and selection. And if time permits, Dr. Shi may also introduce the concept of stability selection and for the selection purposes, and how to use that in the high-dimensional regression.
Okay. I want to make a, sorry,
yeah, sure, please go ahead.
We're still one of the packages that's required is yet compiled on the GCP. So if you want to follow along with the code that's not currently up to date, it should be within a half hour. So, yeah, just as a heads up for everyone.
Okay. Thank you so much, Richard. Okay, so well, first of all, I would like to talk about the background of this high-dimensional model. In the more classic modeling of the data, usually we have, say, a number of objects, a number of samples, which we usually denote as n, and a number of features and a number of regressors, which usually denote as p. In other cases, that the number of the features is less than the number of samples. That's usually called the low-dimensional, or more classic as a regression, or say the theta scenario. In that case, the regression can solve in a lot of scenarios. But at the modern day, as our ability to collect more data has significantly improved, and in all scenarios, we'll have, like for example, hundreds or say thousands of subjects of people, but we collect hundreds, even thousands, or even millions of the features. A very typical example is gene expression. For example, we have the gene expression table, and we can collect the data, for example, for hundreds of patients, and that's already not so easy. For each of patients, if we put the material, collect the material, and put it in the sequencing, say, pipeline, that depends on what's the depth of the sequencing we have, and we can generate, for example, hundreds, thousands, or even say millions of features from it. And by doing that, we still want to collect, for example, whether this gene expression table can be used to predict whether this subject has breast cancer or the infectious disease and so on and so forth. We still want to make this type of connection. And in this case, it's widely referred to as the high-dimensional setting. In terms of high-dimensional, high means the number of features is a lot, and is typically greater than the number of subjects. Okay, I'm not sure if that's clear. No, just that's a little bit background. Okay, and the high-dimensional scenario is important not only in the example I just mentioned earlier, but also in other scenarios. For example, if with the two variables has the collinearity. Okay, so now we want to formally introduce a method called the principal component regression. That's a very typical to solve a very typical scenarios in the high-dimensional modeling and collinearity. Okay, what is the collinearity means? Usually, sometimes the sum of the predictors may have strong linear relationship with each other. We see that the predictors are collinear. In other words, some predictors can be approximately expressed using the linear combination of other predictors. I would like to specifically, for example, give you some example here. We have, say, two features. One is called x2, the other is called x1 here. And for each of those features, x1 is always 1/10 of x2, or x2 is 10 or about 10 equals x1. In this case, that the x1 and x2 behave so similar to each other, they increase and decrease at the same time, and the correlation is approximately 1 here. And these two are collinear. And x4, for example, is approximately equal to x1 minus 2x2 and plus x3. Then the correlation between x4 and x1 minus 2x2 plus 3x3 is approximately 1. And x3 is approximately 1 minus x1 minus x2. So the correlation over x3 and x1, x2 is almost a negative 1. In all these examples, I will say that these variables are collinear. Just imagine in a measurement table, we have the two varies. One is like the measure of the subject's height in inch. Another is the subject's height in centimeter. You can imagine that these two covariates are identical, are the same, essentially same thing. And after, for example, some kind of a conversion, a linear conversion, if you put both of these two variables into your regression model, you want to understand how the patient's height is related to, for example, the patient's BMI. And if you want to do that, then you'll get into trouble. Okay, and I'd like to give some real life example is that in gene expression data. And the gene expression, some of the genes talk to each other. They have a high correlation, and you want to say probably get rid of the some of the gene expressions. So we just give, for example, BRCA1 and BRCA2. And these are two genes that's both highly correlated to the breast, the risk of having the breast cancer. And these two genes, they are related, they are correlated. And another example is antibody levels from the serological assays and the composition of immune cells and the microbiome composition. And for the other examples, I think Dr. Shi will be able to give you more explanation here. Okay. And to illustrate what happens here, I want to use this Obama data, the antibody levels from the serological assays. And this is directly related to the theme of the workshop, the HIV. So first of all, we loading this data set, the BAMA data set. And we use a more complete version of the BAMA antibody data from the case study. Here we will standardize each of the predictors before using them. And what does the standardization means? Okay, you have a data table. For example, each row is the subject, corresponds to a subject. And each column corresponds to, say, one feature. Okay, and some of the features may have higher standard value than the others. Maybe some of the features have more, say, larger scale than the others. I'll give you an example. In the critical care setting that I'm working on, and there are features called the oxygen say, saturation. It's SpO2, you usually call this. And it's usually a percentage. So it must be a value between 0 and 100%. Okay, 0 to 1. And there are other, say, factors, for example, other features like the blood pressure. The blood pressure is a value usually like from 90 to 100, and yeah, usually this range. If you put these two features together at the same level, they are not in the same level. One is like value of 100-ish, the other is like 100 of 0.9 or 0.8 or 0.95-ish. They're not comparable at all. And what do? Usually we will like to do the so-called standardization. By standardization, I mean each of the column, we subtract its mean and then divided by the standard deviation. Okay. We'll talk about why we need to standardize the predictor later. Okay, and then for this BAMA data, it has many features, totally 104 features. We just listed here, and if you want to code, yeah, this you can find out. And here's the picture to illustrate the color key and for the histogram of these values, as well as the pairwise correlation, and the correlation, pairwise correlation between these features. Yeah, usually the red means higher correlation, blue means let's say negative correlation. And you see that this has a chunk of variables. They are all highly correlated. We have another chunk of variables. They are all highly correlated. Okay, which this is pretty common when you talk about the genetics or say genomics data. We have tens of thousands of features, but there will be a lot of repetition. Yeah, some of the gene expressions are essentially representing the similar concepts, similar things of the body. So one feature is high means another feature is probably very high as well. One feature is low means another feature is probably low. So in that case, like that, we have this 4 features here. They highly correlated to each other. Okay, and so any questions so far about this plot heat map? All right, so if we have highly correlated features, then is there any consequence if we just ignore it and directly apply regression? The question is that if we do that, the exact correlationality to make it impossible to estimate the regression coefficients in linear regression. Let's give a very extreme example. Can we estimate the regression model yi equals to beta 0 plus beta 1 xyi1 plus beta 2 xi1 again plus epsilon I? Okay, so the question is that beta 1 xi1 plus beta 2 xy1 means that beta 1 plus beta 2 xi1. Okay. If we know x1 plus xy1 plus x12 is 2, we don't know if it's 1 plus 1 or 0 plus 2 or negative 1 plus 3, and so on and so forth. There's no way we can identify if these two features are identical. We are not able to identify whether this feature contribute to the final effect or this feature contribute. Okay. Well, this is exactly we don't really have the answer to that question. Okay. And then we have a strange interpretation of the regression coefficients. Okay. Now, if we have two covariate x1 and x2 on a regressor, they have a strong linear correlation. And here that the meaning of the beta 1, the coefficient in front of x1 is that if other variable change, keeps steady, and x1 is increased by 1 unit, and y in average increased by beta 1 unit, that's the typical interpretation of the linear regression. Okay, now if x1 and x2 are strongly related, have a strong linear relation, yeah, and then it is not realistic to have the x1 increased by 1 and x2 they unchanged. Usually x1 increased by 1, x2 will also increase by some amount. Now, then if that happens, you really don't have this interpretation at all, and then it makes the regression say meaningless, yeah, less meaningful. Question?
Yeah. So if x1, x2 are the same in the model, does that mean they both contribute to the?
Great question. That's a great question. Here, it is possible that beta 1 is 1 and beta 0, or beta 1 is 1 and beta 0 is 2. It is also possible that the beta 1 is 0 and beta 2 is 2. So you have, from this regression, from this y and xi, there's no way we can tell that which one contribute. It's possible that you contribute, it's possible that I contribute, but there's no way to distinguish.
I'm thinking of these in terms of like, if this was, no, we're not quite at PCA yet, but these are like loadings for PCA, you know, I think these are components that go into that, you know.
Yeah.
If they both correlate with each other, to properties do.
Yes.
Then you think you'd want them both to be represented as contributing equally, kind of, right? I mean, it's like you said, like inches and feet. You take, you know, height and inches and height and feet. Those do both contribute. Yeah. Lost on where the information is lost if you have them correlate. That makes sense.
Yeah, that makes sense. If these two variables both are strongly correlated, it is possible that say feature A contribute, and then feature A, then because feature B is correlated with feature A, so it's also increased. It is also possible the other way around. Feature B is the one that really to contribute.
So, are we talking about like causation? You say contribute, or do you mean like within the actual? Maybe I'll catch on.
Yeah. So far, it's not about causation.
Yeah. Right.
Right. Okay.
Is it possible for study region if you're looking at like longitudinal data, you have like multiple time points? Is it possible for features to be correlated in one time point and not correlated at another time point?
It is possible. Yeah. If it's the case like you explained, then the overall feature of x1, x2 will not be correlated. Yeah, will not be that strong correlated.
Oh, okay.
Yeah, and if that's the case, then at least in that case we used, for example, the longitudinal study. Yeah, that's the situation we can handle. Okay, any other questions? So a third thing I want to mention that if x1, x2 are highly correlated, actually the estimation of the regression coefficient will be unstable, and usually will give us, if we just calculate the effect, and we will have very wide confidence interval for our estimation. The confidence interval is wide means that usually we have a very large p-value, we do significant test, and so on and so forth. Okay. And then let's see, this is the code here. And our y here is HIV in the week 28. And then we input all the variables in then we do that. And here we have this outcome table from R. We have estimate and the standard error here. You see that because of the correlation, a lot of standard error actually is pretty big. Yeah, the estimation is like a 3, -3, but the confidence interval is like a 5 to 10 to the 5. The estimation is -3, but the confidence interval, the standard error here is 5.105 plus 2 times 10 to the 5. That basically means that what we estimate is basically I'm not confident at all. R is not confident at all to give this value. Okay. We really have to do something to avoid that kind of situation. The idea is that we should first of all want to determine the collinearity. If these variables are collinear, we want to get rid of some of the variables and use the other thing. So here, first I want to talk about how to detect the collinearity. We want to basically check the condition number of the correlation matrix of the predictors. So that is if the matrix of predictors is X, then the correlation of this predictor is called the condition number kappa here. The definition of condition number kappa of any matrix is the ratio of the largest singular value over the smallest singular value. And now if the kappa is, okay, this is the largest singular value over the smallest number, because we know the largest singular value must be greater than or equal to the smallest number. So this kappa here is greater than 1. Usually the meaning of this kappa is that the larger kappa, the more collinearity there is in the predictors. And what is the largest possible number? Positive infinity. Is it possible to have a positive infinity, say condition number? The answer is yes, we could have that, which means that the largest singular value is non-zero, but the smallest singular value is 0. So some value divided by 0 is infinity. What does this mean? And when kappa equals to infinity, that means that there is the exact collinearity. There must be, say, one variable equals to some combinations of the other variables, and this variable should be removed because of this collinearity. Okay, and then the general. Okay, so here that I have mentioned that the larger kappa, right, the more collinearity is. And in our real practice, when we analyze the data, how big is big? Here, I think I want to provide a rule of thumb. Usually we say that when kappa is greater than 225, it's hard to ignore the harmful effect of collinearity in the predictors. We will say that X has collinearity, significant collinearity effect is the condition number or the correlation X is larger than 225. If that's the case, then maybe we should do something. Okay. And then, how about this data set? Let's say the kappa X-mat. X-mat is the matrix of the predictors. And we calculate the correlation. In R, we just say COR means correlation, COR X-mat. And then kappa, here say that the exact equals to 2. Okay, we want to exact the kappa value. And it returns this number 2,824. It is big. It is greater than say 225 certainly. And here that I want to say that the condition number correlation of X is the condition number of the standardized X. Therefore, we say that when X has the collinearity, if the condition number of standardized X is larger than square root of 225. But here, to avoid the confusion, we just talk about the correlation matrix of this your data matrix and this condition number. if this condition number is greater than 225, we say this is a significant amount of correlation. Yeah. Okay, so now this is we will talk about the original X maps, and the correlation is strong. But if we scale it, the scale function means the standardized. Standardized means the divided by, for each of the variable, subtract its mean and divided by the standard deviation, and then we evaluate kappa. Usually you will see a significant decrease of collinearity. And this 53. Okay. What if you check your data? You have your data table, right? And you check the data and found out there's a collinearity. Here, solution is that we can remove some of the highly correlated predictors. And second, linearly combine the highly correlated predictors, and for example, to combine them up. And thirdly, the principal component regression. And actually, it's a fancier way adding them up the predictors. Okay, and third, we'll not cover in this workshop is partial least squares, and this is another method that's widely used. Okay, in the previous class, you probably have, we have probably have told you, there's one method called the stepwise regression. Okay, you put all the variables in order, and each time you decide that this variable should be included in this model or not. If it's included, then it's included. Then you take a look at the next variables. You go this. Okay, so let me ask you this question: if these two variables are highly correlated and they are each of them are significant, then what happens if you apply this stepwise regression? So you have two features, A and B, okay, and they are highly correlated, and you do this stepwise regression. Now, first of all, if A is in front of B, well, can you imagine what will happen typically? Yeah, A will be included. Then because A is included, then the B has probably much less predictive power, then B is not included. And if you switch the order B first and then A second, then that's the opposite. What does that mean? It means that the collinearity will break basically the power of say, stepwise regression. And we want to say overcome that as well. So using the stepwise regression, basically what happens, the final, say, chosen model will strongly dependent on your starting model. Yeah, the order of the variables you input to your algorithm. And using the penalizer regression, the estimate coefficients are also very sensitive to change in model, removal of one predictor and removal of the other observations. Okay, and to overcome that, we want to introduce the algorithm called the principal component analysis. And thank you. I think you mentioned earlier this method. This is the right method to overcome the collinearity here. Okay, so when we talk about the PCA, principal component analysis, I want to first tell you that this class, I'm not giving you a formal definition of PCA because it involves, a lot of linear algebra, which is, I don't think that's a focus for this workshop here. And I just want to tell you the intuition behind the PCA and how to use it using R. And I will only emphasize the use of PCA in the principal component regression. Although this PCA here by itself is widely used in actually a lot of scenarios in statistical analysis. Okay. Here, I want to illustrate the intuition of PCA. I just want to start with something simpler. We have only two predictors. One is called X1 and X1. Another is called X2. Basically, the two gene expressions in the data set we just described to you and Bama. And then, first of all, we only take these two columns, XMAT, and extract these two columns. One is the CD4, ANY, and BRC. The other is CD4, ANY, and BRC, and these two columns. And by this code, we basically extract two columns of this data matrix, and we calculate the correlation of these two columns. The value is big, 0.75. Okay, that's a pretty big correlation. And we can further say draw a scatter plot for these two variables. And the x-axis is variable 1, and the y-axis is a variable 2. Okay. Okay, if we want to get rid of the strong correlation by combining x1 and x2 into one new predictor, what should we use? Okay, x1 plus x2, x1 minus x2, or say x1 times a half and plus x2. Okay, it is not clear. PCA provides a systematic way to decide this weight. Basically, PCA tells us that which combination of the x1 and x2 should we combine. It depends on, say, which A and B combination achieve the largest variance. Okay, subject to A squared times plus B squared equals 1. Okay, now here you may wonder why we want to maximize the variance. If you have two variables, why you want to yeah, because essentially you want your data to be distinguishable, and then you want the outcome or the variable to be different, the variance to be big. Okay. So, for example, if as a teacher, as a lecturer, I think I was always instructed, you give an exam, you don't want to put the exam too easy, so that everyone is 100. You don't want to give the exam that's too difficult, so everyone is 0. You want to give the exam in the very right difficulty so that the good students will get good scores. And so some students may have, say, like some of the background may have a slightly lower score, so that I can tell them that there's something that you need to catch up. Here's the same. We want to select those variables that can give us the largest variability. And those variables are usually interpretable and more meaningful when we do regression and all different type of analysis. Okay. So, and here I think what ensures is that maximize the variance, because the variance basically means essentially means that the amount of information that carries by this variable. Okay. So we want to maximize this variance of AX1 plus BX2, and such AX1 and BX plus BX2 will be the best linear combination of X1 and X2, in the sense that it explains most of the variance of X1 and X2. And then what should we do that? We should apply this PCA here. We still have this XMAT, and with these two variables, use these two columns, and we apply SVD on it. We have this XSVD, and then we only take a look at the Y here, the V of it. It returns the value, 0.707. And this PCA result will tell us that the best linear combination of X1 and X2 is 0.707 X1 plus 0.707 X2. Okay. And what does this mean? Still, we have this scatter plot, right? Basically, it means that we should combine these two variables into one variable by projecting every point onto the diagonal line. And yeah, the code here is a bit complicated. Basically means that we want to say have this exploding one and exploding the two entries, A and X and Y. And the code here, the plot XMAT, means that we draw all the dots here. An AB line is 0A over 2 means that we draw this red diagonal line. Means, and then the new points means that we project each of the points onto this red line. By projection means that if you have a line here, then you have points that can go vertically to this line. Okay, and then after you have finished this projection, then this will give us the points, this red point, this green point on this line, we have the largest variance, and we use the point on the location on this line instead of the location on this plane, and that by doing that, we reduce these two variables into one. Is everything clear so far about this plot? Great.
I ask does this happen to minimize the residual regression? Or does it not happen?
Great question. Yes, we are minimizing the residual thing, basically the sum of squares of this length.
Okay.
Okay. It is.
The process could also be defined that way.
Yeah, the process can still be defined that way. We use one variable that can minimize this. The sum of this green line, the sum of squares of the length of this green line. And I want to point out this is different from a linear regression. A linear regression will still draw a line, and the difference is that each point will go straightly down, vertically down to the line. But here is the projection, so it could have an angle.
Okay.
I wanted to ask, but I'm probably betting on something that's not important, but this new variable that is a combination of the collinear variables, does it have any significance in terms of, so you're combining two different measures, like CD4 and or other component. Does it have any physical meaning? I don't know if that makes sense. Or is it just a number to help us get rid of it?
Okay, yeah. Okay.
Am I making sense?
Yeah, that's a great question. I feel that it's the meaning here is that we have two variables, so they're scatter plots like this. Now we want to reduce these two into one variable, and such that this point projected on this variable will have the largest span. So by doing this projection, we minimize the distance so that we can reduce the amount of information we lost, and we want to keep the variance to be the largest, which means that we want to keep the information onto this variable the best. I'm not sure if that answers your question.
Yeah, I'm just trying to understand the idea behind, why does it make sense to combine this variable, like in a physical sense? Like if you have the question is, can you make apples and oranges? Can you add them up? Right?
Okay.
Yeah, I'm not thinking about it like in a specific.
Okay.
But is it? Why can we do that? Is it because we standardize the metric and now we're adding numbers from variables from 0 to 1, something like that? And the unit of the variable does not matter. Like that.
Okay. Yeah, that's a great question. And yes, you have anything to add?
The goal is to say maybe 100 different dimensions turn it into just one, right? So it's like, I guess it's sort of for high level visualization of the shared features, right?
That's true.
Yeah. The combination idea is not intuitive.
Yeah. Well, I feel. Hey, Richard, you have comments?
What is this actually biologically mean?
Yeah.
So it's
It's a little bit.
You have to figure it out afterwards.
Yeah, yeah, Richard, that's a great point. So my feeling is that it may or may not have a physical or biological meaning for combining these variables. For example, if we add blood pressure together with, for example, the oxygen saturation, and what does it mean? And it's probably not it's challenging to interpret from the data point of view. First, this kind of combination can help us to find from a data-driven way to interpret some phenomenon. And secondly, that sometimes we don't have a physical interpretation, means that does not mean that we can. It is then we apply statistics, or then we discover a biological and statistical, a biological physical rule on it. Then yeah, that's the best. And just recall that, so I have to know that how Newton at the beginning find the Newton's principle. Newton's principle one, principle two. Well, he found that from data, from statistics. They collected for example, you use little wood, the balls, and to do experiments, and they collect the time. For example, that the ball moves from this to that. Collect all these different data, and then use that data and use statistics and to discover some of the principles. And well, so does that answer your question?
Yeah, kind of. I think it helps clarify the question I had in mind.
Okay. Okay.
Yeah. Okay.
Just as a heads up, everything is solved on the ECC. If you want to follow along with that, it should be up to date. The testing. Just so that.
Okay. All right. The next thing is that why we want to standardize the predictors. Still, the example is that x2 and x1 here. For example, x1 is multiplied by 100, and then you will still say draw a histogram of these two variables. You will see basically this. You have a very big fluctuation in the first variable, but a little bit of fluctuation on the second variable. This plot is meaningless. It's not as meaningful than the plot we have earlier here. Yeah. So that's why we want to do standardization to make sure all variables are in the same scale, so make them more comparable. So here is an illustrative example. Here I want to give you a the informal definition for PCA. Okay, we don't want to go into the math. Instead, we want to cover the intuition. We have p variables, x1 up to xp, and the PCA basically looks for the best linear combination of x1 up to xp, so that the PC1 equals to a11 x1 all the way to a1p xp PC, and the PC1 is the first principal component. Being the best, it means that we need the PC1 to have the largest variance among all possible values of a11 all the way to a1p, such that it's a11 squared plus all the way to a1p squared equals 1. So how we find the first variable? We have p variables. We want to find out the one-dimensional projection, or say a best linear combination of this variable such that they have the largest variance. After that, then we want to find the second best linear combination x1 of the xp. The defined is say this PDQ. Being second best, we need the PC2 to have the largest variance of all the possible values a1, a21, a2p, such that a21 squared plus a2p squared equals to 1, and the second PC principal component should be orthogonal with the first one. And then we go through this process one by one, and then in the end we can have them at most to say p principal components. And usually we don't need all of this, and say that we need r the principal components. then we can have this PC1, PC2, PC3, all the way to PCR. Orthogonal to each other, and so correlation among them will be 0, and among the principal components, no collinearity issue at all.
And are we performing this analysis on just the collinear variables, or is it just everything included?
Yeah, we can use it to solve the collinearity, and we can also use it to solve high dimensionality, to the dimension reduction. Yeah, there are different, a lot of usage of the PCA. Collinearity is just one problem, one issue the PCA can solve.
Sorry, I meant correlated.
Yeah.
Is the PCA analysis on the correlated variables only, or is it on the entire data set?
Okay. Yeah, you can be both. Yeah, if you identify the correlated variables, then you can use the PC to combine them. And in general practice, to apply PC on all variables as also is widely used. You can, so basically you can apply in both scenarios. All right, so let's talk about the implementation of the PCA. The singular value decomposition is the key component of PCA. And here, what's the SVD? You have a data matrix, the X, and by evaluating the SVD, basically means that you decompose the X into U times D times V transpose. And the D here is a diagonal matrix. Diagonal means that only 1, 1, 2, 2, 3, 3, 4, 4, and those entries can be non-zero. The other entries are 0, right? And the D basically stores the singular values of this data matrix X, and then we say they are D1 all the way to DP. And the DK here quantifies how much variance the K's best linear combination is. Therefore, D1 square greater than D2 square all the way greater than DP square, and the DK square, and here we define this quantity called the DK square divided by D1 square all the way to DP square is the variance in X that can be explained by the K's principal components. Okay, there's D here, and the next is the V. V is the right. It's usually called the loading matrix. The V here is equals to V1 up to VR, so basically the R columns. And each V1 will be the values of AK1 or AKB. That basically stores the combination, and we evaluate it here. So here, basically A11 all the way to A1P, we evaluate it here, will be the first column of this V here. And then A21 all the way to A2P will be the second column of the V here. And then we move on, we'll move along, say, and so on and so forth. And this is the V is the loading matrix. It measures the contribution of each variable into each PC. And next, so we talk about the score matrix. So UD equals XV is called the score matrix. The UD is equal to principal component 1, principal component 2, all the way to principal component C. Principal component R here is the J's column constraint of the value of PCJ. Okay, so this is the implementation of the PCA, but I think it would be helpful for us to look at the code here. And we focus on the variables ending 1078. So we basically collect all the variables here and construct the X mat. And then for this X mat matrix, in order to do the PCA, first of all, we calculated the SVD. In R, the SVD function is called just SVD. And the return of the SVD includes they include a lot of the information, but the most important one is the U and D and V. The return of the SVD is the list. List is the important the object in R language, and the most important the component of this list is the SVDU, SVDD, and SVDV here. Okay, and then if we want to calculate the D and the singular values here, we just input D, and then we have this output. The singular value here is there are 5 of them. They're listed here. And for each variable, we want to find out that the percentage, the percent of variance can be explained by each of the principal components. What we can do is D squared divided by the sum of D squared. D squared means that we still have this vector D, but each entry is squared. And sum of the D squared means that we take a summation of all the entries of this vector. And then this is what we have. What does this mean? It means that the first principal component can explain 60% of the variance. The second is 19%. Third is 9%, and so on and so forth. It just decays very quickly. And next, the loading matrix V. We just include the V here. And this is the loading matrix. As we mentioned, each column of the loading matrix means the weight of the variables. And these are the first PC, this is the second PC, and the third, and so on and so forth. And the score matrix is the map matrix and times V here. Okay, and next we'll talk about after we apply this PCA and what we can do. And is there anything interesting we can play for it? So this is the way we apply SVD to calculate the principal component. But you can see that we can use the other method called the other software package called the PRC, PR count. XMAT, huh? Please, question?
Are there 10 samples going down the road, or there's 10 components?
Okay, let's see.
If you did code on that metric.
Oh, yeah.
Yeah, that's right. That's right. Yeah, we have more than 10. So we only output the first 10 here. Yeah. Okay, the next is there's actually in R to use the SVD is the more, I would say, the more fundamental way to handle this. There are more convenient way to do that. Use the package called the PRC OMP, PR comp, and we input this or matrix here, and we have this res PR. We can evaluate the singular values here. Yeah. And here are the singular values. And for the loading matrix, we can just get it from extract the rest of PR and use the code called the rotation here. Okay, and this is very convenient because not only the 5PC was listed, and it also includes the name of the variables. I would say that SVD is a more rudimental way to do the PCA, but if we use the more developed package called the PR comp, then you can immediately see that the variable names are also included. And here again, that the score matrix had say res PR X and the top 10. And next is the regression with the principal components. And I think the goal what I mentioned is to do regression. We have a data matrix, and we have some of the, whether the subject has disease, those labels, and we want to combine these two. And assume that, for simplicity, we have these two, plus x1 and x2. And we know that the PC1 is 0.707, x1 plus 0.0707 is the best linear combination of x1 and x2. In the sense that it explains the most variance in x1 and x2. And we can use PC1 instead of both x1 and x2 to predict say, the final variable here. Okay, then we have this X-math matrix, and extract these two columns. And then we apply this PC comp, X-math 2x, we have this PC value. Then we apply the GLM, generalized linear measurement, the GLM function. The model is that HIV week 28th value versus the first PC of the PCA result. And the family is a binomial, means that we want to, because the number of cases is an integer, we want to use the binomial model to handle. And then we get this outcome. Okay, and then GLM here, we have coefficients estimate. The PC value here is in particular is 0.1272. And the standard error is 0.1679, which is not so big. And here that the intercept is significant, but this PC value here is not significant. And then we have this, the final estimation regression will be logit of your outcome is equal to minus 1.6188 as the intercept, plus this coefficient times the PC1. And what is PC1 here? PC1 is the combined variable. It's not a individual variable. The PC1 equals to, say, 0.707x1 plus 0.707x2, and then times say this weight, and then that's it. And next, for the linear regression, these steps can be done using the R function, the PCR. And the example below is just for illustration purposes. And here, we still have this IgG, this variable, and we use it to against the PC value 1 here. And here next time we use the GLM, this time with the LM, so the regular least square function. And then we have the residual, the coefficient, and so on and so forth. Then, yeah. And then we can actually calculate the coefficients for both of variable. It's the variable, the weight of this variable times the weight of the component. Okay, and this is how we run the PC regression in 2 steps. First, we get the PC and then apply the linear regression. Actually, we can combine these two into one way. Is just use the function called the PCR. The PCR means the principal component regression. And here is the Y. It's the IgG variable, and then the 2 variables here. And we say the coefficient, we set the number of components to be 1, and the intercept to be, there we want to include the intercept, so intercept equals T here. So yeah, this is our outcome. So if the number of subjects is greater than the number of variable, number of features, we will run the PC regression with all the principal components, and the result should be the same as the linear regression. if you have 5 variables, you say that we want to include all 5 PCs, then actually the 5 PCs and the 5 variables are the same, and then your result will be the same as the linear regression. Yeah, and yeah, this is the code of the implementation here. Yeah. So yeah, this is how we implement so-called the principal component regression. Okay, these are codes and the outcomes. Any questions? Okay. Then the final things I want to talk about is the more general procedures. Suppose we have X, which is X1, X2, all the way to XP or P predictors. Each XJ solver has been standardized, and we want to decompose X using SPD decomposition. Yeah, and get the principal components and estimate the regression of Y, say equals to gamma 0 plus gamma 1 PC1 all the way to gamma n PCn plus the other predictors. Well, the number of principal components n is chosen using methods we described later. Suppose the estimates are gamma 0 hat all the way to gamma n hat. Then we can obtain the estimated regression coefficients for x1 up to xp this way. x1 up to xp here is equal to loadings v1 all the way to bn and times the gamma 1 hat all the way to gamma n hat. And then if we have this regression model, then we have this regression model. And here is the code implementation. Actually, not that challenging. First of all, we do the principal components regression here and summarized. So now you can see that the variable names are called the PC1, PC2, PC3, all the way to PC10. Let's go back to your question. What is the meaning behind this PC1, PC2, and PC10? It's reasonable to do that. We do have this type of concern. So usually what people do is to transform this PC1 all the way to PC10 back to the original variables or original predictors. And the idea is to do basically a matrix multiplication. And here is the code for illustration here. The loading matrix times the coefficient of all the PCs. By doing that, we can transform the weight of the variables back to the original values. And here is the outcomes. Okay, here I want to talk about a very important topic. When we do the PCA analysis, how many principal components we should use? There's no, say, yes, black and white answer to that. There's no, well, here it can still only provide you a sum of rule of thumb. Historically, many people suggest if you have a bunch of variables, you want to use a small number of variables such that the cumulate can explain 80% of the variance. In other words, you want to select this m here such that the singular values you calculated earlier, d1 square all the way up to dm square divided by d1 square and all the way to dp squared is greater than, say, 0.8. Say, you want to select the smallest m such that that value is greater than 0.8. Okay. And here, I want to show you, say, the code to draw this plot. Then we have the d here, then basically this, we can plot the d over sum d, and also call it the cumulative sum of d and sum d. And here is basically the plot here. The number of principal components, the first one usually explain the most of variance, and then this value decay. And then the number of principal components, and then the percentage of variance, the cumulative. So when you have no principal component, so this value is 0. If you include the first principal component, you can explain about this amount of the value, and then so on and so forth. And when it reaches a certain threshold, let's say 80%, and then yeah, we reach the target, and then probably that's the right amount to stop. And I want to say that yeah, this is not the only way, principal component regression, and the other ways like cross-validation can be used to choose the number of components, which we will discuss later. And you can choose number of components such as R-square of the linear regression exceeds a certain level, like 80%, and something like that. And due to some various reasons, only the first principal components is used. And that's, for example, one summarized gene expression scores that represent all the genes expression, or one summary questionnaire score for several questions in a questionnaire. You may group your predictors according to biological context and use one PC from each score. And maybe we should have a break. So actually, do you want to directly join?
Oh, did you just take a break or have you not?
No, we haven't taken any break yet. Probably we should take a break. It's already 1 hour. Yeah.
Okay, go.
Yeah. Thank you so much. And Dr. Shi will take over.
One question real quick.
Uh-huh.
Is there any like disadvantage to the PCR and then back calculating the original
coefficient?
or is this basically just strictly better than doing the linear regression? Because this takes into account co-linearity.
Well, it's for some of the situations you cannot really run linear regression because you have so many collinear. The result is going to be unstable, and maybe you don't even have enough sample size for the number of variables. Mm-hmm. So those are the situations that you can only run PC regression, not the regular linear regression. When you can run both, then the disadvantage of running PC regression is that you have to reverse back to that coefficient, and to get p-values for those coefficient is going to. I don't think the software itself is straightforward.
Okay.
Yeah. So you sometimes you just interpret the coefficient for that PC component directly. Like you can say that this is like an aggregated variable for CD4 cells, and then the coefficient you may not be able to interpret the sign of the coefficient, but you can interpret on the p-value. Like you will say that this is definitely associated with the outcome.
But they do lose some information on the coefficient.
You do. Okay. Yeah.
Yeah.
Okay, thank you very much. Yeah, please take a break.
All right, we'll keep going. So, you're basically at this point where we were talking about how many principal components to choose, right? Later on, we'll talk about cross-validation, which can be used to choose the number of principal components. You can use the number of the variance, the proportion of variance explained, and you can also just use one principal component for a group of variables that you care. So suppose you have several variables that you think are strongly collinear, but the other variables are fine, then you can just aggregate those collinear variables into one by taking the first PC of those variables. So for example, I'm just giving you guys the code to do it. I did a for loop. In the feature matrix, in the data matrix, you can see that the features mostly fall in line with those 4 groups. There are CD4, CD8, IgG, and IgA. I took the PC within each group. So there will be 4 PCs, and the first PC for each group, and you can see that the first PC in CD8 is most associated with the outcome. So this is one way of doing the analysis. You can do it multiple ways. You can take the PC all over all of them. It depends on like where your collinearity come from. And a very informative thing to look at is the heat map we show in the very beginning, where you can see those block structures. This one. So these big blocks, the big red blocks, they are the strong correlations, and those are where you probably want to make the principal component analysis. So the drawback of doing principal component regression is that first, it doesn't help you choose variables. It will use all of the variables to compile them, so you don't have variable selection inside. And second, when you do PC, when you're doing principal component analysis, you're actually not using the Y. You're not using the outcome to compile the Y. You compile the X. Sorry, you compile the X first, and then regress that onto Y. But when you compile all of the X, you didn't use any information from the outcome. So the variance the direction that you explain the most variance in X may not be associated with Y. It may be some directions that are not explaining a lot of variance in X that is more associated with Y. So you may lose information while you do the PC regression. Does that make sense? And if you want to do the compiling of X with Y informing it, then partial least square is an alternative option. It will do a linear combination of the X that is mostly associated with Y. So that will help you compile X in relation to Y. No feature selection, and then principal component regression can be sensitive to outliers because when you're looking for that maximum variance direction in this scatter plot, if you have a bunch of outliers somewhere, it will drag your major variance axis. And then, like I said, you don't have direct output for the p-value for each individual predictor. You have a p-value for the PCs, but you don't have direct p-value for each individual predictor, and that involves some algebra to reverse back. So that's why many people just interpret the PC directly. And when you do the PC regression, there's an option in the function, I think PCR, that allow you to do the standardization of the variables inside that function, or you can do it outside of the function yourself. But it is important to do that standardization to make sure that the PCR is doing that standardization. And after you do the standardization, you may want to, if you decide to reverse back to each individual predictors and interpret each individual predictor, then you also probably want to reverse back the scale as well. So, for example, here, if you reverse back, you have a coefficient like this one for CD4, this one. The coefficient is this, so it's the effect on Y when you increase this one by 1 unit. But this 1 unit is after standardization. You have to reverse back to its original unit. And the formula is given here. You basically have to multiply that. You need to divide or multiply. So the coefficient, this is the original scale. This is the one for the PC. So if you want to get the original, you need to divide your current coefficient by the standard deviation. Any questions?
With this term, the rightmost term is uniqueness, right?
Yeah.
And then the mean X would give you a unit.
Right. So this part will become part of the intercept. You mostly interpret the slope, which is here. This is beta on the original scale. This is beta on the PC. This whole chunk is your PC. So the coefficient for the PC divided by the standard deviation will become the coefficient for the original scale. The p-value will stay the same. P-value is invariant to the scaling. It's just the coefficient and the standard error of the estimate will both change. So the next one is penalized regression. What are the, wait, I don't have the coefficient showing up. the parameters. But this is theta with a hat. So why do we want to do penalized regression? The first motivation is a bias variance trade-off. So let's suppose that we're trying to build a model that estimates a parameter and or predict an outcome. So you can actually think of the parameter estimation and the prediction in the same framework of they're both your target, and you're trying to build a model to get that target. So that target, we're going to use theta to represent it. That's our goal. It can be a prediction or an estimation of parameter. The theta is our goal, and we're trying to use a model to get it. The model will get us the theta hat for model n. We can have multiple models. And we're going to see what model estimates the theta better. But what do you mean by better? So here we're going to use the mean square error. Assuming it's continuous, you take the difference between your estimate and the target, take it squared and expectation. This is your mean square error. This is quantifying how well you're doing estimating your target. And if you use some statistical theory like algebra, then you can decompose this whole quantity into two parts. You will have the bias and the variance, and this is the variance of your target. This is nothing that you can control, because this is like 0 if you have a fixed target. If you have a moving target, this is going to be the nature of the target, but you have no control over this. So essentially, you're going to try to minimize this variance term and the bias term. So the whole estimation is going to be the accuracy of your estimation is going to have two parts. One is the variance, like how volatile your estimation is, and the bias, like how far away you are from the target. It's like how big your net is and how far away your center of the net is from the target. Like you're trying to catch a fly with a net. The net is bigger. That means the variance. Well, that's not a good metaphor, but it's like the So when you're throwing a dart, you try to aim at the center. And if you try to aim at a little place off the center, then that's your bias. And how stable you are throwing that dart, that's your variance. So how good you are going to hit the target depends on how well you aim and how stable your hand is. Does that make sense? So your aim is the bias, and how stable your hand is the variance. And there's actually sometimes a trade-off between the bias and variance. For example, if I collect 100 samples from this normal distribution, what would be the best estimation for the mean of the normal distribution? You were taught to use the average, right? To use the average to estimate the mean. So suppose that we are going to give it a little flexibility and estimate it using alpha. This is just a parameter, like a value that I'm going to choose later, and I'm going to use alpha average of y, this thing as the estimator for my mean parameter. And if I calculate the variance and bias of this new estimator, you will see that essentially the accuracy of your estimation is going to be this whole quantity. So we'll skip all of the algebra, but this is the accuracy of your estimator here. If you make alpha equal to 1, then it's the accuracy for mean. If you take alpha equal to 0, then it means that if I use 0, it will be a bad estimator, and the accuracy of this estimator is going to be mu squared. Does that make sense? If you guys getting lost.
What is alpha again?
Alpha can be any number. So I can use half of the mean as an estimator. I can use mean as an estimator. I can use zero as an estimator. It may be a bad estimator, but it's an estimator.
And how does it compare to the bias?
So if this is not 1, then this is going to be a bias estimator. So the bias of this estimator is this quantity. If it's not 1, then it's going to have a bias. But the variance is going to be smaller if your alpha is smaller. So if I use mean to estimate it, I have 0 bias, but a large variance. If I use half of the mean to estimate it, I have a smaller variance, but I have a bias. So this is going to be the trade-off between the variance and bias. The green line is a bias, the blue line is the variance, and the red line is the bias and variance added up. And the x-axis is the value of my alpha. So if my alpha is 1, then it has no bias, but a larger variance. If my alpha is 0, then it has a smaller variance, but a big bias. So somewhere in between is going to be the best estimator for your mean parameter. So it turns out that if this is your criteria to judge whether how good an estimator is, mean is not your best one. It's actually half of the mean. That's the best one. So the reason why we always use the mean instead of half of the mean or like a shrinked version of the mean is because we value the unbiasedness a lot. But in some of the situations, focusing on too much on the bias may actually make you less favorable estimator if you think this is the thing that you want to minimize.
If like intuitively you just want there to be no bias.
Right.
Much variability as there is. And trying to decrease variability, introduce bias. I guess that would give you more solid data. It almost like, is that not worse data in a pretty important way?
Well, you are given a data set. You cannot increase the sample size after you already get the data. And in some of the data, your signal may be very weak. And it's better to fit no signal than estimating a weak signal that is like really volatile.
Okay.
So that's one motivation. When you do the penalized regression, the linear regression itself is unbiased. But penalized regression will introduce bias. And when you have a very small, weak signal and a large like noise, then doing penalized regression will introduce the bias and decrease the variance, and it will overall give you a better estimation of the coefficient. And the second motivation is for high dimensional regression. When you have the sample size smaller than p-linear regression doesn't work, penalized regression will allow you to include the number of predictors at most equal to your sample size. So you can include more predictors in your model up to the number of, no, that was wrong. So you can include more predictors than your sample size to penalize regression, like so. And then for model selection, so it's going to help you. The penalized regression will actually shrink some of the regression coefficients to 0. It will do variable selection for you, so you will end up with a subset of predictors that is mostly associated with your response. And some people will actually say that they use penalized regression for collinearity, but that's not true. When you have strong collinearity in your data set, using penalized regression is not going to work very well. You need to address the strong collinearity first before you use penalized regression. So when you use penalized regression, it will select variables for you. And if you have two variables that are very similar to each other, then the variable selection procedure will not be able to tell which one is which one. So it will probably select this one half of the time, like the other one half of the time, and you will be confused about which one is the most important one. So in the back to the case of estimating the mean, if you estimate the mean with, if you estimate the mean parameter with the average, is actually minimizing this whole quantity. So it's minimizing the difference between the observation and the mean parameter, this sum of squares. If you try to minimize it, you will get y bar. But for penalized regression, you add a penalizing term back here. So it's going to say that I want my beta to be slightly smaller. Beta hat to be slightly smaller. And it will be estimated with this one. So it's not going to be y bar anymore. It's going to have a coefficient in front of it. And you can control how large this is by controlling the lambda there. Lambda is the penalizing term. It will be one of the coefficients you will see in the R output. So if you rewrite the variance and bias trade-off using the parameters here, using lambda instead of alpha, then the shape will look like this. The penalty parameter at x on the x-axis, the variance, the bias, and the MSE on the mean square error on the y. Your trade-off will give you lambda here, and you can directly plug it in here, so it will be your estimation of the mean parameter. Any questions?
Yeah, so earlier, there's linear regression, which is the regression not working if there's more predictors than observation.
Yeah.
In this context, observation would refer to those are people and predictors are like these factors, like on 7A expression or something. So like in the case of RNA seq data, for instance, predictors would be genes.
Right.
So often, that is the case, we have a lot more predictors.
Yeah.
Okay.
Yeah.
So that's true of regression, not necessarily PCA.
For linear regression, you just cannot. It will not run with a smaller than number of predictors. Yeah. But you can run the penalized regression with more predictors than the number of samples. Yeah. So this is if you plug in your remember we are drawing samples from a normal distribution. The mu is the mean of the normal distribution, and the sigma is the variance of the normal distribution. So it turns out the best estimator you can get to estimate the mean is going to be this thing, and multiplied by your y bar. It's not exactly half. So the one I show you was half because I had the mu and sigma set up in that way. It's this number multiplied by y bar. So you're shrinking your mean estimation slightly towards 0. So now you have a slightly biased estimator, but it's smaller variance, and overall it's a better estimator. And you can see that this quantity has a big important contributor, which is the mu over sigma ratio. You can divide the numerator and denominator by sigma. It will give you the mu to sigma ratio. This thing is also called the signal to noise ratio. So if your signal is stronger and your noise is lower, then you can afford an estimator that's closer to mean, to y bar. If your signal is very weak and your noise is very strong, then it's actually better for you to estimate it using like more closer to 0 than y bar. you shrink more, you penalize more when you have a weaker signal and a larger variance. When you shrink less and go more toward the linear regression side if you have a strong signal and a small variance. And here, you can see the sample size is also here. So the signal is also related to your sample size. If you have a lot of samples, then it enhances your signal as well. So the signal is like the strength of your effect, the sample size combined, and the noise is how noisy, how variable your observations are. So if you have a more spread of the data, it means larger variance, you might want to penalize more. If you have a larger sample size, you might want to penalize less because it's stronger signal. So it's important to keep in your mind that when you have a data set, like how strong your signal is. Do you have a lot of biological signals in there? Do you have a large sample size? If those are not true, then you might have a weak signal to noise ratio, and those are the situations when you want to use penalized regressions or things that can help you enhance the signal. But in real life, nobody really knows what this exactly is. So you will have to rely on something like cross-validation to tell you how much to penalize. And you will use training data to estimate and use your test data to evaluate how well it estimates. And you will penalize at different scales and see which penalizing scale gives you the best prediction or estimation in the testing data. And there are three main types of penalized regression: ridge, lasso, and elastic net. So remember that we were trying to minimize the distance in linear regression. We're trying to minimize the distance between your observation and the linear equation, right? This is the observed y. This is the straight line we're trying to fit, and we're trying to minimize the difference between your observed data point and the linear line. This is minimizing this will be linear regression. But if you add something saying that I want my coefficients to be slightly smaller, I don't know by how much, but I want to penalize them. I want to shrink them a little so that I can have a better overall performance. And that shrinkage is achieved using this sum of squares of the coefficients. If you add the sum of squares, this is ridge regression. If you add the absolute value of your coefficients, then it's lasso. If you combine both, it will be elastic net. The difference between those is that for this one, you are trying to penalize on the beta in this way. It's a square curve. So it will penalize more on the larger value. But for this one, you're penalizing it with like a upside down pyramid shape. This is your curve. And this curve has a little sharp point on the zero origin. If you penalize using this, it will actually produce a very nice property. It will shrink some of those beta exactly to zero. This one will not produce exactly zeros for beta, but this one will produce zero for some of the betas. So it will, for lasso, it will actually perform a variable selection for you. For ridge, it will not. Ridge will help you estimate a data set when you have large, small sample size compared to the number of predictors. They can both work for that, but only lasso can do the variable selection. And elastic net, combining both, can also do the variable selection. This lambda here, the larger it is, the more you're shrinking your parameters to zero. And generally, it will be large if your noise is large and your signal is weak. A good value of lambda can be chosen using cross-validation. If it is zero, it will just fall back to linear regression. If it is super big, it may just shrink all of the coefficients to zero, so no predictor is useful for your outcome. So the difference between ridge and lasso, like I said, lasso can do the variable selection. It will give you a sparse estimation of the coefficients because some of them is 0, some of them are not, so that's sparse. But ridge regression has some nice property as well. Lasso's solution is not algebraically tractable. You cannot write out the solution. But for ridge regression, you can write it out and you can actually get the variance estimate. You can get the p-values. But for lasso, it takes a long way to get the p-value. So people rarely use lasso to get p-values. They mostly use it for variable selection. Using elastic net, you have the benefit of lasso to select variables. You also have the benefit of ridge regression, which is you can include more predictors than the number of samples. So when I say penalized regression works for more predictors, it's going to solve your problem with sample size smaller than the number of predictors. But the final model fitted by lasso, it will only have at most the number of the predictors that are the same as the sample size. So ridge regression can include more variables in your end model than lasso. Any questions? So if you have a variable selection that's in your mind, you might want to use lasso. If you don't care about p-values, you just want variable selections, then lasso is better than ridge. If you still want the p-values and the tractable inference, then you need to use ridge. There's really no good combination of both getting variable selection and getting your p-values. Unfortunately, it's super difficult. Doing variable selection and getting p-value, those two are very difficult to combine together. Anything? So elastic net is the combination of both the lasso penalty and the ridge penalty. These two parameters, the lambda and alpha, will be the things you specify when you run the in R. I guess those are already talked about. When you implement penalized regression using R directly, using the provided function, you don't have to worry about scaling and centering your predictions. But in any case, if you have to work with a statistician to write the ridge or lasso yourself, then you need to standardize those predictors as same as the principal component regression. So the implementation of ridge or lasso or elastic net is through the function grmnet. This is running all of the predictors that are CD4 on linear regression. Right now, I still have enough sample size to fit a regular linear regression, and you can see that this is the p-value, right? But if I run penalized regression, this is a function grmnet. The input syntax is that you have your predictor matrix here, you have your outcome vector here, and this alpha will tell R whether it's running ridge regression or lasso or elastic net. If it is 0, then it's ridge regression. If it's 1, then it's lasso. If it's somewhere in between 0 and 1, it's ridge regression. You can specify it any number you want. If you really want to choose the best alpha, you need to do a round of cross-validation yourself, but it's complicated. Most of the times you probably will just run these two, the ridge and the lasso. And the output you will get is a matrix of the coefficient for each lambda. Lambda is the tuning parameter, the penalizing parameter. how much you want to penalize on your coefficient. You can see the larger your lambda is, the more the coefficients come to 0. And for ridge regression, it's a smooth trail. They slowly get to 0. For lasso and elastic net, they will actually go directly to 0 at some point. So suppose that cross-validation tells you this is the best lambda to use to penalize, then all of the variables that come to 0 before this point will not be inside your final model. The variables on the right will be kept. The variables on the left will be thrown out. That's a data-driven way to select variables. And elastic net here looks quite similar to lasso, but if you change the alpha in your, if you change the alpha from, if you change your alpha from half to something closer to 0, but not 0, you may have it behaving more like a ridge. So you can change the value of alpha to get something in between the first two. This is alpha equal to 0, this is alpha equal to 1. You can tune your alpha based on your data. Any questions? It's a little taxing because it's a very counterintuitive concept at the very beginning. Why am I using something other than mean or other than the center of the net to catch something?
Are there any obvious situations in which, you definitely want to do like penalize regression rather than any kind of regression?
When you have more predictors than sample size and you have no way to cut down the number of predictors, then penalized regression can help you select them. And then it can help you estimate, at least give you an estimate of the coefficient, and do prediction as well. If your focus is on prediction, any of those will help you. If your focus is on getting like a subset of predictors out of the crowd, then lasso or elastic net will help you. Ridge regression, I believe you can run it with more samples, more predictors than sample size, and it should also give you a p-value. So the main reason for running penalized regression is when you have more predictors than sample size. A secondary reason is even if you have enough sample, but your signal is very weak, and you have a lot of, like, suppose I have 10,000 samples and 1,000 predictors. I can definitely run linear regression, but how do I interpret 1,000 predictors? I may want to shrink them down into a subset, and lasso will help me select that. And then it may also give you a better prediction if your noise level is really high, because when you're not penalizing them, you're here. You can see that like a lot of them are not very significant. But it's because you're throwing a lot of garbage in your model, and the garbage will increase the standard error. It will decrease the accuracy of your estimation if you have a lot of garbage in there. And lasso is going to impose this penalty here. It's saying that if your estimation is a garbage, then it go to 0. I will only keep the ones that are not garbage. And here you can see as you increase your penalty, as you try to penalize more on the garbage, then more of the variables will go to 0. And eventually all of them will go to 0. But you will need to use cross-validation to choose the best place to penalize them. I need to leave 20 minutes for the survey. So I probably will not take another break before that. Cross-validation is a very general framework. It's a concept, it's like a framework, a concept of like a philosophy that can help you choose the tuning parameter in your model, or choosing between different models. It's like you have a machine, you throw your X in there and you produce a Y. And you have several machines. And you're trying to see which machine is the best. The difference between those machines can be dramatically different. It can be a linear regression for one machine, a random forest for the second one, or it can be very similar, like a penalized regression with lambda equal 1 and the penalized regression with lambda equal 2. Those are all machines that suck in the X and produce the Y. And how do we evaluate how well they are in terms of producing an accurate Y? That can be evaluated using cross-validation. So the main idea is that I'm going to split my data into training and testing. Use the training to establish the X-Y connection, and use the testing to predict the Y on the testing data. So your training data is going to build the connection between X and Y, and then you can use that connection, use your testing X to produce the testing Y. Does that make sense? The X-Y connection is your machine that sucks in the X and produce the Y. But when you break your data set into training and testing, you want to use all of this data points as the training at least once, right? You want to use all of them as testing at least once. So that's where this is where you will see the term like 5-fold or 10-fold cross-validation. So for example, I'm doing k-fold, then I randomly split the sample roughly equally into k subsets. And I will use one of them as the testing, and the k-1, the remaining them, as the training. The bigger one as the training and the smaller chunk as the testing. This is like a diagram for that. I randomly split the data into 5-fold. I will use one as testing, one as the training. I will use the training to build my machine to establish the X-Y connection, and then I will put my testing X into the model, get my testing Y. So my Y hat and my Y are both from testing, and then I will check how close they are. The error between the amount between Y hat and Y in the testing data is this error. So this is evaluating the error on the prediction of this chunk when you build the model using the gray chunk. And then I will do it for another way. This is the testing, and the other four is the training to train the model. It will probably choose a slightly different estimation for the coefficients or selection of the variables, but it will also give me a prediction of the Y. So each chunk is used as training 4 times, and each chunk is used as testing 1 time.
What is the proportional? Is like 20 to 80?
No, 5-fold is very commonly used, or 10-fold is very commonly used. It depends on your sample size. And there's a very special kind of cross-validation is when you only have one sample here and all of the remaining as training. In this way, you will use each testing once, but your model is built on eliminating one of the samples. So each time you build a model, you throw away one and predict on that specific one. It's called leave one out cross-validation. It has some special properties, and one property that I really like about it is that it doesn't have randomness involved. When you do the 5-fold split, you can do many ways of splitting your data into 5-fold, right? So when you do the split, you may have lambda selected to be 1 to be the best, but if you do the random splitting again, you may have a slightly different lambda. So you might want to record how you split your 5-fold, but with leave 1 out, there's no randomness in there. You always leave 1 out.
I've also seen randomly choosing, not like maybe a fifth of the total, but each time it's from completely random sample, and not from this chunk and then totally separate chunk and totally separate. You know what I mean? Like,
so you're saying that I'm not going to record what I chose as testing before, and every time I'm just randomly sampling like one fifth.
right, yeah.
You can also do that, but it's not going to guarantee that each sample is going to be used as testing one.
Okay.
So in this way, everyone's prediction error is going to be accounted for here. And in each fold, you will have a prediction error for this red chunk, and you will average all 5 of them. That will be your cross-validation error. And you will do this process for each value of the tuning parameter. For lambda equals 1, you have an error. For lambda equals 2, you have an error, and you choose the lambda value that has the smallest error. When you compare linear regression or random forest or different machines, different prediction models, you will have, they can be very different models, but they will all produce a cross-validation error. And the smallest is the best.
I think the principle behind what I'm talking about is that you could do like 100
Yeah.
different runs, as long as each one is validable to a bunch of different randomly selected pieces. I guess probably better than just doing 100 tweet chunks that don't have overlap.
Yeah, this non-overlapping way really guaranteed.
Okay.
And the number of folds you choose is typically 5 or 10 or leave 1 out. Those are the most typical ones. And the more you use, the more folds you use, the slower it's going to be. So leave 1 out is going to be cumbersome if you have like 10,000 or like super large lump sum of that. But it's quite common for biological data to have small sample size. So leave 1 out is quite nice. So the leave 1 out is when you split them into the same number of sample size. And if you use cross-validation but not leave 1 out, then it's a good practice to set the seed so that you can repeat the same analysis on your laptop, or save the sample population so that other people can repeat on their machine. And to do this for lasso or other penalized regression, you can use cv.glmnet. The setup is going to be the same as the penalized regression part. It's just going to allow you to do the cross-validation and choose the number of folds. The first 3 terms are the same. And if you do the plot of this cross-validation output, it will produce this cross-validation error curve. So for each lambda value, it's taking a log lambda. Each penalizing parameter is going to correspond to 1 cross-validation error, and it will help you find the smallest point. And this smallest point will, this is how large the lambda is, and then you can obtain the coefficients corresponding to this penalizing parameter. So it's actually, this is for Verge. It's going to produce this estimation of the beta. None of them is exactly 0. So if you use lasso, this is lasso. Lasso's penalizing parameter is around here. And the result will be a sparse vector. So using lasso is going to select those variables as non-zero, and the others are all shrink to 0.
Are those the
Yeah, those dots are 0.
Why did it just like 0?
It's a smart way for R to save sparse data. So if you have a large matrix, and you want to store it in R's memory, in your computer's memory, you can store the whole matrix itself, like each entry is one number. Or you can, if you have a sparse matrix, for example, your whole matrix only have 3 non-zero values, that's 1, 1, 1, 3, 1, 5, then you can just store 1, 1, 1, 3, 1, 5, those 3 pairs, and their corresponding values. The others are all 0, you don't have to store them. So these dots represent 0. This is the sparse way of R saving the data. Other questions? And if you want to do the prediction, because most of the times with variable selection, you run into a difficult decision on how to do inference, and it's like I said, there's no good way to combine both variable selection and inference, the p-values. So most people would use this just for variable selection or for prediction purposes. And to do prediction, you can just use the predict function on the cross-validation outcome, and you can tell them what is your criteria of choosing a lambda, whether it's the lowest point of the curve or something else. And then your predicted y, you can compare it with your observed y. On the x is the observed value, on the y is the predicted value. For this specific data, the signal is super weak. It is not a strong linear relationship. So that's why when you do the lasso variable selection, most of them are straight to pretty close to 0. Like even this one is pretty close to 0. In some situations, you may have all of them straight to 0. Your cross-validation curve may just be a decreasing curve. It means that none of your predictors are useful. So including them actually make your out-of-sample prediction worse. Garbage predictors make your out-of-sample prediction worse. They may make your in-sample prediction better because you're going to overfit, but your out-of-sample prediction will tell you which one is really useful. Garbage will actually make your prediction worse. So it's not always collecting more variables the better. And you can have, before this, we are running the lasso regression for linear models. You can also have a penalized version for logistic regression. You have penalized version of linear regression, and you will have a penalized version of the logistic regression. And the implementation is almost the same, except that you have to specify family to binomial. This is telling R to use logistic regression instead, and you will need to have this thing to be a binary variable. And here we're trying to, so XMAT is all of the CD4 predictors, and the binary outcome is whether that person gets infected or not. And this is the ridge. This is the prediction versus the observed labels. It's doing okay. Your predicted probability of infection and the infection status, you have a higher probability of infecting for the really infected one. So it's concordant. And for lasso, it's going to penalize here, and the coefficients are here. So still, a majority of them are not really helpful in the prediction perspective. And if you do the predicted, if you plot the predicted probability versus the real infection status, it's like this. If you want to compare your lasso model with your ridge model, then you can write your own code to perform the cross-validation yourself. It's going to be fun, but not a simple task. And this is when we do the elastic net. So there's really no way to know which one is best. Someone said that no model is correct. Some are useful. If your focus is really on prediction, then you can always use cross-validation, this out-of-sample prediction scheme to evaluate which model is better. But if your focus is on inference, like how significant a predictor is, then penalized regression will not help you much. And cross-validation can also be used to choose the number of principal components for PC regression. If you do it for linear regression, then there's a built-in way of running it in R. You just need to use GCR function. This is for linear outcome PC regression, and it will help you plot this cross-validation error curve. So you can specify what is the criteria for the evaluation. You can choose R squared, but I think this is the mean square error. That's our focus. So the lowest point is where you would choose. For this specific one, I'm running the continuous outcome is actually the IgG GP41. This XMAT is all of the CD4 cells. So I was like predicting how much antibody there is using the CD4 count. And it turns out if I do principal component on all the CD4 variables, only one of them is the most predictive of the IgG antibody. So my best option is actually choosing one. This will tell you how many of the components is most useful for the prediction. And you can also use R squared as the criteria just to choose the number of components. That's by specifying validation type equal to R squared. This will run it and produce all of the curves for you. You just need to use this output in the validation plot function. Just specify what value type you're trying to plot. It will give you this curve. For R squared, the larger, the better. For cross-validation, the mean square error, the smallest is the better. So you can also see that this curve is not like monotone or smooth. It's because when you do principal component analysis on the X, you do not guarantee the best information is in the front of the PCs. Some of the good informations are in the back, and they may be in the second or the fifth or the 10th. And whatever component that is associated with Y is going to get you this job. So from here to here, from 9 to 10, it's going down because the 10th principal component is helping. But from 1 to 2, it's getting worse. So all of these added in is not as good as just using one. But in some situations, you may have the lowest point later. It really depends on like which of the components has the most relevant information on Y. So it's zigzag.
You can't reorder those without code, but line of code.
You want to reorder it?
Based on like when you're putting, can't you reorder the principal components so that the most important they are arranged in order of like ascending order or descending order?
That's a very interesting suggestion. You're basically suggesting doing variable selection on the PCs. You can do stepwise regression with the PCs. I didn't cover that. There's a thing called forward stepwise regression, where you add one predictor at a time and see if that's going to help you or not. And when you add the predictors, you search among all of the remaining ones instead of adding them as the first DC, second DC. Okay, you can definitely use that. Combining the principal component analysis with forward stepwise selection.
So that's called stepwise.
Yes. It's a quite traditional way to do variable selection. But I think you need to be cautious about the p-value. Whenever you do variable selection, and you need to be careful about the p-value. Some people will use lasso, for example. I guess I'm pretty much done with the materials here. So suppose that lasso tells you these are the important variables. It's tempting to rerun a linear regression with just those 4 variables, right? You use lasso to select your most important set, and then you fit a linear regression on the most important set. But the p-value in that linear regression model is going to it's actually going to be too optimistic, because your linear regression, when you have the p-value, the p-value of the standard error is accounting for the variability in your data. When you run linear regression only on these 4 variables, you are already eliminating some of the uncertainties in the data. So your linear regression accounts for the variability involved only in those 4 variables. It's not accounting for the variability you're having when you do the variable selection. So that p-value is actually already too small. The real true p-value should be slightly larger than that. And to get the true p-value involves very complicated statistical model. I don't think we have like a optimal solution for that. So you can refit linear regression on those 4 variables. You just need to be careful about the p-value. You can probably interpret on the coefficients, but not the p-value. Unfortunately.
And you cannot use the p-values of the original set. Say, picture that pops up here, the p-force was significant in the original set before the reduction in the feature fraction. Does that change in the new setup?
If you can already run your data set with that variable and get the p-value, then you don't need to use the P-lines regression, right? No, let's talk it out.
Yeah. You're saying that this regression here will give you
this penalized regression help to select those 4 as
remind me that they give you p-values for this?
No.
So then how do you, and then you're saying that the calculation of p-value, the real p-value that is would be difficult,
Yes. You can rerun linear regression with these 4 predictors. It will give you a nice p-value, but that p-value is over optimistic. Right. Just with those. But if you can run all of them, you can still use them. Yeah.
How would you report on that? It would say you selected a lasso, and then you interpret.
You directly interpret it on the selected set.
But you don't say statistically significant or too low.
Right.
Because you know your p-values are too low.
Right. So it's helpful for prediction purposes mostly. And if your focus is on selecting variables, it's helpful. But if your focus is on inference, it's not a good option. And there are methods who can do those called post selection inference. It's just not very. I don't see many good R packages doing that. So you might need to have your statistician doing it for you.
Usually involve like having a different set of data.
Oh, if you have like a training data to do the variable selection and then the testing data to re-estimate the coefficient, then that's fine.
Oh.
Yeah.
You can't do it with the same.
Yeah, it's double dipping. Thanks for the reminder. Yeah. You can use one data set to do the variable selection, the other set to do the inference. So that's cross-validation. It's a very nice framework you can use for any model comparison, tuning parameter selection. And for penalized regression, there's also a quite nice concept called stability selection. Unfortunately, it's also not a good way for you to get p-values, but it's a quite nice concept to get you a stable selection of predictors. When you are knee deep into penalized regression like me, you will realize that lasso is actually sometimes not quite stable. Like depending on how you randomly split the data, depending on how strong your signal is. If your signal is weak, then one randomly split of data may give you a different split of the data may give you a different selection of the predictors. That's where stability selection comes into rescue. So the idea is that you're going to do variable selection still on a subset of the samples, but instead of using cross-validation to check on the prediction performance, you're going to see how often a variable is selected among those subsamples. So every time I'm going to do a randomly draw subset of samples, and I will run lasso cross-validation on this set and select, actually not cross, sorry, go back. Every time I select a random set of samples, I will run penalized regression for every value of lambda. Every value of lambda, I will know whether a variable is selected or not. And then I will do another random set of samples, do the same thing and see if a variable is selected at this lambda value. So if I do this 100 rounds, a variable will be selected sometimes among those 100 rounds. And if like among 90 of them, if 90 out of 100 rounds, this variable is selected, then it is a more relevant one. If only 10% of those rounds, the variable is selected, then it's not important. The philosophy is that you want to have a stable selection of the variables. You want them to, no matter how you split the samples, this variable is still majority selected. So the whole steps are, you subsample, you do it without replacement, and then you do the variable selection within the subset of the sample. This can be done for each penalizing parameter, each value of the penalizing parameter. And then you would aggregate among all those subsamples, like how frequent each variable is selected. And you can choose a cutoff, like out of 100 rounds, if 70% of among 70% of the rounds a variable is selected, then it's considered stable. So this threshold you can choose it yourself. The benefit is that it will be pretty robust to outliers, when you have very noisy data set, it will not give you a it will reduce the risk of selecting noise-driven variables. And it will also be more generalizable because you can claim like even for 70% of the resamples, I will still be able to select this variable. So if I have another data set, then it should also work for that data set, right? So it's more generalizable to subsampling subsampling from the same population. And it's also very flexible. So any variable selection method that you use, you can use this way to check how stable the variable selection is among all of the subsamples. So even for stepwise regression, like the one you add one parameter, one predictor at a time, or for lasso, or for elastic net, or even for random forest. If you use random forest in a variable selection, where you can also use stability selection to check the selection frequency, like how often is a variable selected among all of the subsamplings. For lasso, you have a well-packed package that do the stability selection for you. You will put the predictor matrix, the continuous outcome here, and then you can choose it. You can ask it to fit lasso, or you can ask it to fit elastic net. This is the cutoff probability to plot here. So essentially, it will give you a frequency of a variable selected among all of the subsampling. So the top one with the largest probability means that among about 55% of the subsampling, this variable will be selected.
Good.
I think it's better. My personal understanding is that this is like a feature ranking. It's like the feature importance in random forest. You don't get significance, you don't get a clear cutoff, but you rank them by their importance. So this can be done for lasso pretty straightforward. But if you want to do it for penalized logistic regression, you will have to write your own code. So it's not user-friendly, but I think this whole concept is quite interesting. For biologists, it's important to know that if you change your data set by a little bit, you may have a different conclusion. And if you really want to have a stable conclusion, then this whole stability selection framework by subsampling your data and making sure your variable is important in any subsample, that is a very great idea to experiment on. All right, any other questions? So I'm basically, I'm still scraping the surface of many of those methods. It's still, you probably still find it more convenient to work directly with the statistician to solve this problem for you, but it's good for you guys to understand how they work, so that when you collect your data set, when you work with your statisticians, you know where the weak point is and what are the reasons why we choose these methods instead of them. At the bottom of your lecture notes, there's a sign-up sheet. The evaluation. So post-session survey. This link is different from before. I think we have the survey for all of the sessions, right? So please take some time to finish this survey. I'm supposed to keep you guys here to do the surveys until, and I'm supposed to not let you guys go before you finish. It will really help us improve future session.